Good afternoon, ladies and gentlemen. Let's start the next section, our workshop. And this afternoon, we divided our workshop in two parts. In the first part, we're gonna have two talks. The first one from the Professor Reza Hazagi and from the Professor Valmir Freitas. I'd like to take the opportunity to thank for kindly accepting our invitation. And following, we have the second part with a technical section in which the Dr. Hazagi will be our chair. So the first talk, Professor Hazagi, titled Fault Location in Power Networks Using Time Reversal Theory. Dr. Reza is currently a lecturer, assistant professor at the Electrical and Computer System Engineering Department of Monash University, Australia. He received the PhD degree from the École Polytechnique Fédérale de Lausanne, Switzerland, in 2016. From April 2016 to October 2017, he was a postdoctoral fellow at the EPFL. Dr. Hazagi has been the recipient of numerous awards, including the Distinguished PhD Thesis Award of EPFL, finalist for the €1 million Lopes Laureate Prize, Basil Papadias, I think so, yes, Best Paper Award at the IEEE PowerTech Conference in 2020. And the Best Paper Award at the ESA IEM Conference in 2017. His research on the electromagnetic time reversal has led to a commercial patent. Please, Dr. Hazagi.
Thank you, Mr. Chairman. So before starting my presentation, I would like to thank the organizing committee for inviting me. It's a great pleasure to be here in Brazil. So it's my first time in Brazil. I'm really enjoying it. So in this In this presentation, I will show you our recent fault location method, which is based on a very interesting theory called time reversal. Before starting that, so I'm from Monash University, Australia. A bit introduction about my university. It's the largest and most international university in Australia. It's the best university in engineering in Australia. Also, globally, the ranking is 44, which we are improving also. And it's also located in Melbourne, the most livable city in the world. So I invite all of you to visit us. We will be very happy. At Monash University, we have started recently a very ambitious project with the investment around $135 million. And the idea is to transform our campus to a smart city and a microgrid, with integrating 20 buildings, 1 megawatt of solar panels, 1 megawatt hour of battery, and EV chargers. And the idea is to use the campus as a live lab to test our developments. So let's start the talk. So my talk is about fault location method. Some of you I see are from this field, but many of you don't know the problem. So why we need, what's fault location and why we need to study this problem? So the fault location problem has been studied in our literature for decades. So in fact, the first paper was published in 1950s, I believe. And since then, many, many methods have been proposed, but still there is a big room to further improve the method, especially due to two main reasons. The first one is active distribution networks. So you know now the power networks are transforming from passive networks to active networks by integrating distributed energy resources. And many of existing impedance-based fault location methods might fail when we have these distributed energy resources. So we need to think again about this problem. Additionally, we are experiencing very complex power network topologies now. For instance, multi-terminal HVDC networks, these type of networks like supergrid in Europe, or some examples in China, and protection and fault location is a major challenge to realize such networks. So it still is a very important problem to study. So what happens when there is a fault in the network? So when there is a fault, so first, power networks is very prone to short circuit because we use mostly bare conductors. And due to many events like wind, rain, etc., it's very probable to have short circuits in the network. What happens is when there is a fault, a part of network can experience outage. What we need to do is we need to first find the fault location, repair it, and restore the electricity. And this is the practice we have been doing for decades. As I said, this problem has been studied in literature since 1950s. Many methods are available. If we can categorize them, we can find three main categories. The first one is based on phasors. So these methods, they measure fundamental frequency, or essentially impedance. So as we can imagine, they are very straightforward to apply. However, their performance might be affected by many conditions, like pre-fault condition or fault impedance. Therefore, we decided to use traveling wave-based methods. So instead of measuring 50 hertz, we measure high-frequency signals. So they are more reliable, more accurate. The problem with some of existing traveling wave-based methods is, first, they need high sampling rate, high bandwidth sensors. They need sometimes multiple measurement points, and sometimes also time synchronization, which is complicated. And finally, sometimes they need sophisticated signal processing algorithms like wavelet. And finally, we have the knowledge-based, the third category, which needs still further work to become more practical. So if we have a look on these three categories, for active distribution networks and multi-terminal HVDC networks, we prefer to use traveling wave-based method because their performance is much better than the impedance-based ones. And from practical point of view, we prefer to use methods which rely on single measurement system, meaning single end methods. And this was the motivation we started the research to work on new type of traveling wave-based method which requires only one measurement point. So this problem, fault location problem, how is it managed in reality and in practice is many places, almost everywhere in the world, utilities, they use devices called fault indicators or fault passage indicators. They're installed in various points in the network. When there is a fault, they start to blink, to flash, the ones towards the fault. Then the utilities send the crew, they essentially drive along the lines, they do visual inspection, and then find, okay, where is the fault location? The problem is we need hundreds of devices to be installed in the grid. And these devices, they don't show the location, but the path and the span. Then we need to find the location by doing visual inspection. And finally, it can take hours, on average 90 minutes. So to find a solution, we proposed a technology, we call it GridGuard, and instead of having hundreds of devices in the network, we only have one device installed in a substation. And this device can protect a network zone. I will define the zone later. So we use only one device per grid zone, and we can pinpoint the exact location with a precision of few meters. And we can do it in few minutes, 1 to 3 minutes on average. And the secret behind that is a theory called time reversal, and the rest of presentation I will talk about that more. But before explaining the time reversal, first let's see what is time. So time is a very interesting concept because when we say what's time, everyone knows what we are talking about, but to give an accurate definition is very difficult. So we know time has one dimension, so it's simpler than space, which has 3 dimensions. And the first mathematical expression for time was announced by Galilei and then formalized by Newton. And then later, Einstein related time and space with the relativity, so we know that. But very interesting definition was given by Pascal. So Pascal defines time as a primitive word. It means it belongs to category of the concepts that are so fundamental, we cannot provide any definition. Now, we had always this question in history, can we go back in time? So the answer is yes, but for some specific laws, not for everything in the universe. So it's interesting to see most laws in physics are time reversal invariant, meaning they are symmetric over time. So we can go back in time. Example is Newton's law. or pressure wave in acoustic medium. So both of them, they are time reversal invariant. So we can go back in time. We have other examples which are not time reversal invariant, like second law of thermodynamics or entropy. But what is more interesting for us is to see if electromagnetic waves are time reversal invariant, because they are the all the concept behind wave propagation and transmission line, and also everything behind electricity. So let's have a look on Maxwell's equation. These four famous equations. I apply time reversal, meaning I change t to minus t. And if I look carefully on these equations, what I understand is these equations are time reversal invariant if I have these two hypotheses. J becomes minus J and H becomes minus H. But this has a physical meaning and physically correct, because if we inverse time, we go back in time, the velocity of charge, electric charge, they change the sign. So it means the current density changed the sign. So J becomes minus J. And if J becomes minus J, the magnetic field also will change the sign. So all this has a physical meaning and physically correct. So essentially, it means Maxwell equations are time reversal invariant. So we can apply time reversal. If we are able to apply time reversal theory, we can use very interesting concept called time reversal mirror. So to explain it, it's very simple. Imagine we have a source, any type of source, which emits waves. And let's suppose we have number of sensors which are able to record these waves. This was our first step, direct time. In the reverse time, if we time reverse these waves, back inject to the same system, we can reconstruct again the source. So essentially, it's kind of time machine. We can go back in time, and we can reconstruct the event. Okay, let me show you animation, which explains this much better, if it works. So here, imagine this is a swimming pool, and we drop a stone on this location. And we have 4 sensors which are recording the waves. So we drop the stone, and now we are recording the waves. Then what we will do in the second step is we will time, okay, don't stop, sorry. If I find a way to use my mouse, camera. Okay, I need to repeat again the video. For some reason, it's not working. Yes, good. So now I'm back injecting the time reverse one to the same system. So it's very important to keep the system topology unchanged. And you will see the back injected signals will focus again on the circle, which was our source. I don't know why it's not working, but trust me, it focus on the circle. So we can reconstruct the source, right? And this was an example for electromagnetics, which is kind of, we can extend it to the traveling waves. But let's have a closer look on our specific problem, which is the fault location. So let's suppose we have the telegraph equation for a single conductor lossless transmission line, described by this equation. I apply the time reversal operator, I change t to minus t, and I have this second equation. So since I only have second order time derivative, this equation is symmetric over time, right? So it means it is time reversal invariant. What it resolves is if we have a signal recorded at a given point in the network, like voltage or current, we can time reverse this signal, meaning we will have another signal, but this signal also holds in the system equation. Very, very interesting peculiarity of the time reversal theory is that in animation, I showed you I used 4 sensors. But if we have a closed reflecting medium, meaning if my waves don't escape the medium, I can use the process effectively using 1 sensor, meaning 1 measurement point. And this is interesting for us because in power networks, the lines are terminated to transformers. So essentially, we have kind of close reflecting mediums, and we can use the theory for using single observation point. And finally, time reversal is defined in time domain, but we can extend it to frequency domain by applying the complex conjugate of the Fourier transform function of the signal. Okay, now I will show you how we apply it for the fault location problem. We need to consider some hypotheses. The first hypothesis is that I told you we need to keep the topology of the system unchanged. However, when a fault happens in network, it changes the topology. So it means probably we cannot able to apply it, but there's a very important feature here. In the reverse time, when we don't know the fault location, right? So what we do is we define number of guessed locations. If our guessed location matches the true fault point, in that case, both medium, both network will have the same topology. And only in that case, the theory will hold, and we will have the energy concentration. And we will use this property to develop our method. So how is our method? I use a toy example to explain it. It's a single conductor lossless transmission line terminated to two transformers, and I have a fault in some point in the along the line. So I do the analysis in frequency domain. So I need to consider some hypotheses to simplify my calculation. The first one is the line is terminated to two transformers at the extremities. And to simplify my calculation, I replace transformer with two high impedances. Then I assume I'm able to record the fault-originated signals at both ends of the line, meaning UA1 and UA2 are my sensors. I assume the line is lossless, so the attenuation comes from all the terminations, and also I have a steady-state pre-fault condition. Some more assumptions. The reflection coefficients, I assume they are frequency independent to simplify my calculations, and finally, the fault is modeled with a step voltage source. UF is my fault at XF. So by applying this voltage source at XF, first I find UA1 and UA2, the voltages at both sensors in frequency domains. I do a little bit math, and I find these two equations. Then in the second step, I need to replace these sensors with sources, right? And by applying the time reversal. So UA1 complex conjugate and UA2 complex conjugate are my time reverse signals. I use Norton equivalent to simplify my calculations. And what I find is fault current at each guessed fault location. So my unknown is guessed fault location, right? And I don't know where is it. So what I do is I move the location from beginning to the end of the line, coordinated to XF prime. And for each XF prime, I find the fault current, IF, as a function of XF prime. And I know from the theory and the animation I showed you, if XF prime becomes XF, I will have energy concentration. Let's see how it works. This is an example. Line is 10 kilometers. I apply a fault at 8 kilometers. So in the first scenario, I record the waves at both ends. And this figure shows the energy of the fault current as a function of guessed location. So as we expect, at 8 kilometers, we have a peak, which is our fault point. We did something more interesting. So we removed one of the sensors, and we only kept the one at the left. And again, we are able to find the exact location. At 8 kilometers, we have the peak. And this confirms we can use the theory only with one single measurement point. So it was the frequency domain, but what happens if we want to apply it in reality, in time domain? So it's very simple. In the first step, we record the fault-originated transient signal in one measurement point in the network. Then the unknown, as I said, is the fault location. So we define number of guessed locations in the network. We apply time reversal, we time reverse the signal, and for each guessed fault location, we simulate the network by back-injecting the time reverse signal, and we find the energy of the fault current. And we know only at one point energy will have peak, and that is where our true fault location matches the guessed fault location. Let's see another animation, how it works. So again, I considered my toy example, 10 kilometer line, and the fault happens at 8 kilometers. And this is the voltage I record in this substation, the voltage signal. Then, second step, I time reverse my voltage, and I divide my lines for different guest fault locations. For each one, I simulate the network by back-injecting the voltage source. So what you will see here is the back-injected signal. This is the fault current at different locations, and this is the energy. So let's see what happens. So now I'm back-injecting, and I'm calculating the fault current at different locations. And I remind you the fault was at 8 kilometers, so have a closer look on 8 kilometers. So you see at 8 kilometers, as we expect, the current has highest amplitude, which verifies the whole thing I said. So the whole thing I said up to now was valid for lossless lines. What happens if the line is lossy? So it's a little bit more complicated. I won't go into details, but if the line is lossy, so we will have additional terms in the telegraph equation for the losses for R and G. And they make, unfortunately, the equations not time reversal invariant. They can be time reversal invariant only if we invert the losses, meaning we consider minus R and minus J. It doesn't have a physical meaning, but mathematically we can do that, right? So we did a very interesting study, and we analyzed the impact of losses on the performance of the method by considering 3 backpropagation models. The first one, we invert the losses. So in this case, we know the equations are time reversal invariant, so we can apply the theories without any problem. We consider a case where we neglect the losses, and a case when we have lossy medium, the same losses in the both phases. What we found was very interesting. To summarize, so when we neglect the losses, the method has some errors, which we expected, but both lossy and inverted loss models, they provide exact location. And this means also we can extend this theory for lossy medium. So how we validated the method? First, we did a reduced scale experimental setup. In our lab, we built a small power network using coaxial cables, used high-speed MOSFET to create a short circuit between the inner conductor and the shield, and different type of network, like T-shape, like this one, straight line, many, many others. And what we found was very interesting. First, the method is able to find which section of the network is faulty. So here you see energy along this path and energy along this path. So this one shows higher average energy. So we know which section of the line is the faulty one. Then we can find what is the location on that section, faulty section. So this was the first experimental setup we did. Then we did simulation case studies for numerous type of networks, like mixed line, overhead line, underground cable, different fault types like three-phase, face-to-face, face-to-ground, high impedance, low impedance, and the method worked perfectly for all of them. Also for more complicated networks like IEEE 34-bus test feeder, we use only one device installed in the substation. We simulated the network for different types of faults, again, three-phase, face-to-face, different fault impedances, and the method was able to find the location. For series compensated transmission line, the same method applies. We used one measurement only on the left side, although we had the capacitor in middle of the line. And using only one measurement, we were able to find the location. And finally, for multi-terminal HVDC networks. This was a very interesting example because in all the previous ones, the protection system is not really fast. So we have enough time to record the full window of the traveling waves. In multi-terminal HVDC network, the protection system is extremely fast, 5 to 10 milliseconds. So before recording the full window, the breakers, they open the line. So we did a study to see the impact of the time window duration on the accuracy of the method. And it was interesting to see, even with like 10, even with 5 milliseconds of the time window, the method works without any problem. So after all this offline analysis, we started developing a prototype using this method. And this is the schematic of the prototype. It had two main components. First, the fault triggering and acquisition. So detecting if a fault happens in the network and acquiring, recording the waveforms. And then FPGA-based real-time simulator. Why? Because if you noticed, in our method, we need to do multiple inspection to simulate multiple times the network. So this can be time-consuming if we want to use a PC. What we did instead, we developed a real-time simulator, our own real-time simulator on FPGA. So I won't go again through details of this one. I'm happy to discuss later. But this is the structure. We use National Instruments Compact Trio platform. If you are not familiar, so these are embedded controllers. They have CPU and an FPGA. So we use CPU to pre-process the data. So essentially, we use EMTP-RV. It's a simulation environment as a graphical user interface and also as a benchmark simulation software. This software generates a netlist file. And we read the netlist file in this platform. And then we develop all the information like nodal admittance matrix, everything, transmission line model inside the FPGA model. So first we validated the real-time simulator. This is the simulation results for a fault voltage recorded in a station. Comparison of our results with EMTP-RV. So as you see, they match very good. And the system was simulated in real time with an integration time step of 5 microseconds, which is not possible with Opal RT or RTDS. Then we did another one. We developed the real-time simulation model of a three-phase inverter. And we did a very interesting test in France. We connected a controller generating a PWM signal, feeding both the real-time simulator and a physical inverter. And we compared the output current of a physical inverter with our real-time simulator. So you see they match very, very, very closely, although we had noise and many, many other issues. And for this one, the simulation time step was 150 nanoseconds, much, much lower than the commercial real-time simulators. So using the real-time simulator, our own real-time simulator, we did a hardware-in-the-loop test for multi-terminal HVDC network. We did 370 fault cases, only 6 cases, less than 2%, the system failed to pinpoint the exact location. And thanks to the high-speed computation of the FPGA, the average execution time was 60 milliseconds. For three-phase network, radial one, we did the same hardware-in-the-loop test with more tests, 866 fault cases. Only 13 ones the system failed with some error. And at the end, what we did, we took our prototype and we installed it in a live power network, medium voltage distribution network in Europe, in Switzerland. This is the single line diagram. This was the substation where we installed the system, and this was the feeder we did the test. It was a very challenging feeder because it was composed of 2 parallel lines in one pylon, 66 kV and 18 kV coupled. And also it was composed of different overhead and underground sections. Very, very mixed line. Some photos. So this is our system installed in the substation, and this was the substation. It was also a rainy day, very difficult to do the test. And we tried it with different cases. So the utility helped us to create physical short circuit between conductor, ground, phase conductor and ground. So they had circuit breakers to generate fault. And this was the location our system was installed, and this was the location of the fault, like 10, 12 kilometers far away. So first we tried with the permanent fault, 0 impedance. This was the voltage we recorded. After that, the system automatically started doing the process, and this peak corresponds to the exact location of the fault. So we were able to distinguish and identify the location. Then with the zero crossing, because traveling wave-based methods might suffer when the fault happens at the zero crossing, the method, fortunately, worked without any problem. For high impedance faults, so we increased the fault impedance for 67 ohms. Again, we were able to find it. And finally, for a transient fault, not a permanent fault. And we were also successful in this test. So yes, this was my presentation. Before finishing, so I'd like to invite you to submit paper. So we are organizing a special session next year in Auckland, in IEEE Measurement and Instrumentation Conference about fault location. So you are more than welcome to submit papers, and hopefully we'll see you there. Thank you very much.
Thank you so much, Dr. Hazagi, for your excellent talk. So we have time for questions.
Congratulations for a very interesting presentation,
Thank
Dr.
you.
Reza. I am very happy for having you here in the WCNPS.
Yeah, thanks for inviting me.
And I am very happy to see that you are working on a so interesting theme, because I think the fault location today here in Brazil is one of top 3 subjects to be treated by protection engineers. I have a lot of questions. I will try to do one that I think that is more relevant. Sometimes when you are studying the fault location problem, we have to simplify the system around the monitored line. I saw that you have to resimulate your system after taking the signals from the actual one. And I would like to know a little bit more about the effects when you consider some simplification, like modeling part of the system like an equivalent, even equivalent, in which we can't properly simulate the propagation of traveling waves, even knowing that this propagation can result in another pattern on transient.
Okay, very important questions. Thanks for asking. So first, I said we need one device per grid zone. What I mean by grid zone is part of network which is confined within 2 transformers. Why? Because the traveling waves, they cannot pass the transformer. So if you have a transformer, we need to repeat again the system. But the rest of the network within 2 transformers, we need to model it in our simulator. But we simplify a lot. For example, we don't model transformers. We represent transformer with capacitors, because it's the high frequency model of a transformer is represented by capacitive behavior. Or for lines, we don't use frequency dependent line model. We use Bergeron model, constant line parameter. So we do all this simplification in order to be able to simulate a network in FPGA. Otherwise, it will be very, very difficult.
Okay, thank you.
We have time for more questions.
I'd like to know where the algorithm of localization was implemented.
Okay, so it was implemented on this compact trio, the National Instruments compact trio. But the FPGA was simulating the network, and the CPU, the microcontroller, was taking the measurements, the currents, calculations, and applying the energy calculation, etc. So the post-processing was happening on the CPU, but the simulation was happening on the FPGA.
On the FPGA. And what about the communication between the FPGA and the real-time?
So we were using FIFOs, the DMA FIFOs. Yes,
okay.
Memories.
Okay.
Congratulations on the very interesting work.
Thank you.
I was wondering, you mentioned that to identify identify the fault location, you have to guess.
Yes.
And I was wondering, what's the impact of the guess that you make, the grid or the fine.
Yeah, I understand. So
Okay.
the more we have a guess location would be better, we will have better accuracy, of course, if we can do it with the high resolution. So we have done the test. We can even go less than 1 meter of fault location accuracy. If we define guess fault location within 1 meter resolution. But it's not practical because it will take a lot of time to simulate. So usually, for example, in the pilot test, our guess location on average were displaced 200 meters.
Okay.
So this was the first theory we proposed. Then we presented an extension of this work. And instead of doing multiple simulations, instead of guessing the location, we can do all the process in one shot with only one simulation. I didn't present it here because the problem with that one is it works only in frequency domain. So we are trying to extend it also for time domain.
All right. Thank you.
We have time for more questions. Felipe?
Okay, we have time, no problem. Are you using voltage signals?
We use voltage signal. We can equally use current signal. It doesn't matter.
I am asking that because it's a very important improvement on fault location based on traveling waves, because we usually try to avoid the use of voltage signals due to the CCVT frequency response. So it seems that your method solves this problem.
Let me show you. Thanks for asking this. So this, oh, you don't see it. So we didn't use normal CCVTs. What we did in the pilot test, we used these sensors provided by a company called Altea. They manufacture high bandwidth medium voltage sensor, relatively cheap. So like for three sensors, we paid 1,500 euros, and the bandwidth is 5 megahertz. So we use this sensor, and they're active sensors, so they don't have any saturation problem, etc.
Okay, thanks.
But we can use current as well, without any
No problem.
difficulty.
Only one more? I'm sorry. And about the uncertainties in line parameters.
Okay.
I don't know if you consider like a range of values that you can choose.
So we were always afraid of the uncertainty because we need the line model. But in the pilot test, what we noted very interesting point. So the utility, we did the test with them. They didn't know, they had some ideas about overhead section. So they had the plan, but they didn't know anything about underground cable because they constructed the cables 50 years ago. So they knew typical type of cables, but they didn't know the exact. So we considered some assumptions, and it worked. But we are doing some research on that to see the impact of uncertainties on the performance of the method.
Okay. We have time for one question. So I have one question.
Sure.
Actually, have you ever tried to use the time reversal theory in other applications of power system?
We tried it once because there was some interest from a utility company to locate lightning strike. And it was very similar to the fault location problem. So instead of locating fault, we were locating the strike point on the shield. And also if a flashover happens on the insulator, we were able to find also the flashover. Because that's important for some operators to do some maintenance, etc. We tried it, yes, for the lightning as well.
Okay.
But this theory started from not electricity, from acoustics. So if the wave equations are time reversal invariant, we can apply it without any problem.
Okay. Very, very good. Congratulations
Thank you very
once
much.
again.